Here we're going to go through Lenz's law examples. 3 examples we're going to go through here just to show how things work. Now, first of all, this one, which we kind of gone through before, I'll quickly go through it again. We can use Lenz's law to predict the direction of EMF and hence current by knowing that force opposite to the one pulling the bar out is needed, since the direction of an induced current is such as to oppose the course producing it. So we know the restoring force is to the left, so restoring force is going to be in that direction. So placing our fingers in the direction of the magnetic field, so we're going to put our fingers in the direction of the magnetic field. Now our palm is now pointing to the left for the opposing force direction. We see our thumb is now pointing in the direction of the induced current. So because we're opposing that force, our fingers are in the direction, using the right hand rule, our fingers are in the direction of the magnetic field. Our thumb then points in the direction of the induced current. So that's one example. On this one, we have given a force pushing the loop around in a counterclockwise direction. We've got a force here, we're showing the velocity here, and it's pushing this loop around this way. It's pushing it in a counterclockwise direction. Now, using Lenz's law, there is an opposition to this motion. Lenz's law said that whatever happens is going to oppose that motion via force in the other direction. Hence, if we orientate our hand holding fingers in the direction of the magnetic field again, so this time we're going to hold our fingers in the direction of the magnetic field, they're in that direction here, and our palm wants to push that back down, so we're in that direction and we want to push it that way. So if we hold our thumb then will point in the direction of the induced EMF, and that's what we've got there. So that's that one. Then looking at this one, in this figure, when the solenoid current is increasing, so we've got this current running through here now, so we can work out the B field of this current in the same way. If we think about the current going in that direction, then you can see with our fingers are going to point, and on the other side it's going to be the same thing. The current going in this direction, then the field's going to go around and underneath, if you like, underneath. So it's going to go in this direction, and the same on the other side. So you end up with the field going in this direction. So first of all, that current is producing a magnetic field going in this direction. So if we put our fingers going in the opposite way to this flux going here, so if we imagine we're grabbing hold of that ring now, and we're going to put our fingers just around this bit here, so around this side that's facing us, and put our fingers there, you can see that's opposing the magnetic field. Now our thumb then points in that direction, so we know that the induced EMF is going in that direction. Whatever's happening, Lenz's law will always oppose that change in whatever way it can. Lenz's law is also directly related to energy conservation. For instance, in this example here, the induced current in the loop dissipates energy at the rate of I squared R, and this energy must be supplied by the force that makes the conductor move despite the magnetic force opposing its motion. Now, if the induced current were to have the opposite direction, the resultant force on the moving conductor would make it move faster and faster, violating energy conservation.